So in the last video, we started talking about using multiple quantifiers, so more than one existential or universal quantifier to build up a more complicated statement. And now we're going to go through how do we prove any different type of combination of two quantifiers as true or false. So in the first case, we have an existential quantifier. There exists an x and there exists a y that makes p of x, y true. This is going to be true if we can find a single x and a single y. All we need is one single x and a single y, and a single y, such that that statement pxy is true. Looking at this, it looks very messy. My handwriting's terrible. I'm sorry. Just remember there's typed notes on Blackboard. Alright, and how do we show that an existential statement is true? Well, if it's not the case that there exists an x and a y that make it true. So if there's either no x or there's no y, that makes it true. So if there's either no possible x value, that makes it true, or no possible y value, no possible, x or y, or both, that make this open statement p of xy true, then we would say the entire thing is false. Now, on the other hand, if we have a universal quantifier for all x and for all y, p of xy is true. That's going to be true only if the statement p of xy is true for every possible choice of real numbers x and y. And it's going to be false if we can find one counterexample. If we can find an x or a y that makes p of xy false. Right? If we can find a counterexample, then that universal statement would be false. Now, what if we had statements that use both types of quantifiers? There exists for all, or for all there exists. And again, we have to be careful here because having one of them be true does not necessarily mean that reversing the quantifiers will make it true. So in the first case, there exists an x such that for all y, p of xy is true. Overall, remember, this is an existential statement. So to prove an existential statement, you need to find a witness. So this is going to be true if we can find one single x value such that the rest of the statement is true. So such that p of xy is true for every possible y. Alright, you need to provide that single x. So if you're proving this is true, you start off by saying let x equal 5 or let x equal 0, right? Give an actual x value that's going to make p of xy true for every single y that you could plug in. Now, how do we prove this is false? Well, this is going to be false if no single x value makes p of xy true for every y. This is harder to show, right? It's harder to show that no single x value is going to make p of xy true for every y. So to prove that this is false, oftentimes it's easier to negate the statement and show that the negation is true. Okay, so the negation of an exists for all statement would be a for all exists statement. Okay, so let's talk about how to make a for all there exists statement true. So if we want to show for all x there exists a y such that p of xy is true, then we need to show overall this is a universal statement. So we need to give an argument that shows that no matter what x value you choose, you'll always be able to find a y that makes that open sentence correct. So if given an arbitrary x, you can find a y And oftentimes you're finding a formula for y such that p of x, y is true. This is nice because if you're finding a formula for y that makes p of x, y true, then your y value can depend on x, right? So let me make a note here. Y can depend on x. It does not have to be fixed. All right? And to give you an example of that, when we did, let's see, this first example up here, this was a for all there exists problem. We started by letting x be an arbitrary real number, and we found a formula for y. We said, okay, so given an arbitrary x, you're just going to let your existential y, you're going to let that witness y just be equal to whatever negative of x is. So your y value really depended on whatever your particular x value is, right? That only works if you're starting with a for all quantifier. Now, when is this statement going to be false? Well, it's going to be false if there is just one particular x, if there is a single x value such that p of x, y is always false. Okay. So if you can find a single x value so that p of x, y is always a false statement, then we know that this entire statement's going to be false. So let's just do a few more examples together, and we'll do a lot more in class. All right. For all x, there is a y such that x squared is less than y minus 1. All right, let's try and parse this out symbolically. For all x, we can assume this is x in the set of real numbers. There is a y, there exists a y, such that x squared is less than y plus 1. All right, this is of the form for all there exists. So going back, we're looking at case 4 here. For all there exists. So to prove this is true, given an arbitrary x value, we need to find a formula for y, which can depend on x, that makes x squared less than y minus 1 always true. All right, so let's try, I don't know if this is true or false, so I'm just going to try to jump right into proving it's true, and if I hit a dead end, then I'll try to prove it's false instead. So, let x be an arbitrary real number. We now need to show that this existential statement is true. We need to show that we can find a y value so that x squared is guaranteed to be less than y plus 1. All right? Well, can we try to solve this inequality for y? Because remember, y can depend on x. Right? We're trying to show that this y exists, but it's allowed to depend on x. So if I were to try and solve this inequality for y, I would get that y needs to be greater than x squared minus 1. Just subtract 1 on both sides. So if I choose a y value that's bigger than x squared minus 1, then I'm guaranteed to have something that's going to work here for every y. So choose a y value that's bigger than x squared minus 1. Well, x squared is going to be bigger than x squared minus 1. So I'm going to let y be equal to x squared. Now we just need to show that this predicate is always true for it, right? So then we have x squared is equal to y, which is definitely going to be less than y plus 1. This is true. And therefore, our entire universal existential statement is true. In other words, we can prove this by saying, okay, if you handed me any real number x, right, for any real number x, I can find a y that makes this true just by letting that y be x squared. So if you handed me 5, then I would give you the existential witness 5 squared, or 25. Then we have that x squared, 5 squared is less than 25 plus 1, 26. Great, it works. Okay, it's going to work no matter what x you use. All right, so notice we proved that this is true by letting x be an arbitrary real number and then finding a y value, finding a witness that's going to make that predicate true. Let's do another example. For every integer x, there is a natural number y such that x times y is greater than 0. Alright, for every integer x, for all x, there is a natural number y. Ooh, we have to be careful here. For every integer x means for every x in z. We have to include that integers because otherwise they would assume you're talking about real numbers. So for every integer x, there exists a natural number y such that x times y is greater than 0. Such that x times y is greater than 0. Alright, so again, this is a for all there exists. If we were to prove this is true, we would need to let x be an arbitrary integer. It's not a real number anymore because I specified x as an integer. And now we need to find a y, or a formula for y, and y has to be a natural number. It can be a formula in terms of x if we want, such that x times y is positive. Alright, so how do we, can we solve this inequality like we did in the last case? Yes and no. I mean, if I tried to solve this inequality for y, I'd have to get y by itself, which would require dividing both sides by x. Except we can't really divide both sides by x because, well, for one thing, depending on whether x is positive or negative, this inequality sign in the middle might flip. If you divide by a negative, it flips the inequality symbol. But also, x could be equal to 0. Right? If x is equal to 0, I can't divide both sides by 0. That's not allowed. I can't divide by 0. So our usual method of solving for y to help find that witness y isn't going to work here. So let's try to think through whether this is even correct. For every integer x, we can find a natural number y such that the product of x and y is positive. Well, that problem that we had in solving this inequality of saying if x is 0, we can't really solve this because can't divide by 0, that's actually going to help you to find a counterexample. Because we're trying to prove that this is true for every possible integer x. But when x is equal to 0, that existential statement, there exists a y such that 0 times y is positive, that's not going to be true anymore. This whole statement here is false. There's no y that's going to make this true because 0 times y is 0. And 0 is not going to be greater than 0. Right? That's because 0 times y is 0, which is not greater than 0. Right? Which means we found a counterexample, which means we've shown that this statement is false. Okay, now keep in mind, if this statement is false, that means that its negation would have to be true. Sometimes it's easier to show that a statement's negation is true than it is to show that the statement itself is false. So if we had just negated this statement from the start and shown that the negation was true, then we could have concluded that this statement was false. So how do we negate this statement? I could go through each step individually like I did before, but it works the same way where a universal quantifier turns into an existential quantifier and vice versa. And then you also have to negate the predicate. So if I wanted to negate this statement, for all x would become there exists an x in the set of integers, such that, okay, there exists a y in n would become for all y in n. And then finally, we would need to negate this predicate. So the negation of xy is greater than or equal to 0 would be xy is strictly less than 0. Okay, so forget this. This is the negation right here. So if this statement, if our original statement is false, as we think it is, this statement here should be true. How do we show that an existential universal statement is true? Well, we have to provide a witness x that makes this statement always true. And x equals 0, that counterexample for the original statement is going to be a witness for the negation. For x equals 0, we have that for every natural number y, 0 times y. Oh, whoops, hold on a second. Our original statement was xy is greater than 0. I wrote greater than or equal to here. That was an accident. This should have just been greater than, which means the negation would be less than or equal to. Oh, okay, I had a little issue there. Now we have it fixed. So for x equals 0, we have that no matter what y value you choose, 0 times y is equal to 0, which is in fact less than or equal to 0, which is what we're trying to prove. So the negation statement is true, which means the original statement is false, as we thought. All right, one more example. Consider the statement, just one quantifier here. This is a little different. We have for all x, and then our predicate is an if-then statement. It's a conditional statement. If x squared is greater than 0, then x is greater than 0. So this statement says, for every real number x, if x squared is greater than 0, then x is greater than 0. This is what we're trying to show here. It's true or it's false. If it's true, it needs to be true no matter what x value you choose, that if x squared is greater than 0, then x is also greater than 0. And to show that it's false, we need to find a counterexample. We need to find an x value such that x squared is greater than 0, but x itself is not greater than or equal to 0. And in fact, there is a counterexample here. Let x be equal to, how about -5? Then the hypothesis, that is the statement x squared greater than 0, is true. And that's because -5 squared is indeed greater than 0. But the conclusion is false. The conclusion, x greater than 0, is false. That's because -5 is not greater than 0. Okay, so we found an x value that makes this implication false. It makes the hypothesis true and the conclusion false. That's what makes an implication false. And so, overall, this universal statement is going to be a false statement because we found a counterexample. All right, now just a few takeaways from this unit. Remember that a mathematical statement has to be either true or false. There's no in-between. In fact, for some branches of math, they might believe that there is an in-between, but for our purposes, any mathematical statement is guaranteed to be true or false. Also, the purpose of building up the symbolic language that we've been using this chapter is that it allows us to know how to prove that certain types of statements are true or false, which is going to give us a way of proving statements that are sort of a little more interesting to us in future chapters. The conjectures that we're going to try to prove later in the course can be written using the same symbols that we learned in this chapter. So if you know how to prove a symbolic statement is true or false generally, then you have an idea for how to prove that this statement is true in this particular case. So keep that in mind as we move into the proofs chapter, which is chapter 2.